This module introduces DevOps automation, a key factor in achieving consistency, reliability, and speed of deployment. Specifically, we'll talk about the services that support continuous integration and continuous delivery practices as part of a DevOps way of working. With DevOps and microservices, automated pipelines for integrating, delivering, and potentially deploying code are required. These pipelines ideally run on on-demand provisioned resources. This module introduces the Google Cloud tools for developing code and creating automated delivery pipelines that are provisioned on demand. We will talk about using cloud source repositories for source and version control, cloud build, including build triggers for automating builds, and managing containers with artifact registry. We will finish by reviewing infrastructure as code tools like Terraform. Let's begin by talking about continuous integration pipelines. Continuous integration pipelines automate building applications. This graphic shows a very simplistic view of a pipeline, which will be customized to meet your requirements. The process starts by checking code into a repository, where all the unit tests are run. On successful passing of these tests, a deployment package is built as a Docker image. This image is then saved in an artifact registry from where it can be deployed. Each microservice should have its own repository. Typical extra steps include linting a code, quality analysis by tools such as this image is the pipelines. Let's begin by talking about continuous integration pipelines. Continuous integration pipelines automate building applications. This graphic shows a very simplistic view of a pipeline, which will be customized to meet your requirements. The process starts by checking code into a repository, where all the unit tests are run. On successful passing of these tests, a deployment package is built as a Docker image. This image is then saved in an artifact registry from where it can be deployed. Each microservice should have its own repository. Typical extra steps include linting a code, quality analysis by tools such as SonarQube, integration tests, generating test reports, and image scanning. Google Cloud provides the components required to build a continuous integration pipeline. Let's go through each of those. The Cloud Source Repository service provides private Git repositories hosted on Google Cloud. These repositories let you develop and deploy an app or service in a space that provides collaboration and version control for your code. Cloud Source repositories are integrated with Google Cloud, so it provides a seamless developer experience. Cloud Build executes your builds on Google Cloud infrastructure. It can import source code from cloud storage, Cloud Source repositories, GitHub, or Bitbucket, execute a build to your specifications, and produce artifacts such as Docker containers or Java archives. Cloud Build executes your build as a series of build steps, where each build step is run in a Docker container. A build step can do anything that can be done from a container, irrespective of the environment. There are standard steps, or you can define your own steps. A Cloud Build trigger automatically starts a build whenever you make changes to your source code. You can configure the trigger to build your code on any changes to the source repository or only changes that match certain criteria. Artifact Registry is a single place for your team to manage Docker images or deployment packages, perform vulnerability analysis, and decide who can access what with fine-grained access control. Let's go into each of these services in more detail. Cloud Source repositories provide managed Git repositories. You can use IAM to add team members to your project and grant them permissions to create, view, and update repositories. Repositories can be configured to publish messages to a specific pub subtopic. Messages can be published when a user creates or deletes a repository or pushes a commit. Some other features of Cloud Source repositories include the ability to use audit logging to provide insights into what actions were performed, where, and when, and direct deployment to App Engine. It's also possible to connect an existing GitHub or Bitbucket repository to Cloud Source repositories. Connected repositories are synchronized with Cloud Source repositories automatically. Developers gain complete control over defining workflows for building, testing, and deploying across multiple environments including VMs, serverless, and Kubernetes. There is no more need to provision or maintain build environments. All is handled by Cloud Build. You write a build config to provide instructions to Cloud Build on what tasks to perform. These are defined as a series of steps. Each step is executed by a Cloud Builder. Cloud Builders are containers with common languages and tools installed in them. Builders can be configured to fetch dependencies, run unit tests, static analysis and integration tests, and create artifacts with build tools such as Docker, Gradle, Maven, Bazel, and Gulp. Cloud Build executes the build steps you define. Executing the build steps is similar to executing commands in a script. You can either use the build steps provided by Cloud Build and the Cloud Build community, or write your own custom build steps. A GitHub link to a list of available Cloud Builders can be found in the course resources for this module. Build triggers watch a repository and build a container whenever code is pushed. Google's build triggers support Maven, custom builds, and Docker. A Cloud Build trigger automatically starts a build whenever a change is made to source code. It can be set to start a build on commits to a particular branch or on commits that contain a particular tag. You can specify a regular expression to match the branch or tag value. A GitHub link to the syntax for the regular expression is available in this module's course resources. The build configuration can be specified either in a Docker file or a Cloud Build file. The configuration required is shown on this slide. First, a source is selected. This can be Cloud Source repositories, GitHub, or Bitbucket. In the next stage, a source repository is selected, followed by the trigger settings. The trigger settings include information like the branch or tag to use for the trigger, and build configuration, for example, the Docker file or Cloud Build file. Artifact Registry is a universal package manager for build artifacts and dependencies. Artifact Registry can store Docker and OCI container images in a Docker registry. Artifact Registry integrates with Google Cloud's CI/CD services or your existing CI/CD tools. You can store artifacts from Cloud Build and deploy artifacts to Google Cloud runtimes, including Google Kubernetes Engine, Cloud Run, Compute Engine, and App Engine Flexible Environment. Identity and access management provides consistent credentials and access control. Artifact Registry implements a Docker protocol, so you can push and pull images directly with Docker clients, including the Docker command line tool. Google Cloud services that typically integrate with Artifact Registry, such as Cloud Build and Google Kubernetes Engine, are configured by default with permissions to access repositories in the same project and do not require a separate client. Artifact Analysis is a family of services that provides software composition analysis. Google Cloud services that typically integrate with Artifact Registry, such as Cloud Build and Google Kubernetes Engine, are configured by default with permissions to access repositories in the same project and do not require a separate client. Artifact Analysis is a family of services that provides software composition analysis, metadata storage, and retrieval. Its detection points are built into a number of Google Cloud products such as Artifact Registry and Google Kubernetes Engine for easy and quick enablement. The service works with both Google Cloud's first-party products and also allows you to store information from third-party sources. The scanning services leverage a common vulnerability store for matching files against known vulnerabilities. Now, binary authorization allows you to enforce the deployment of only trusted containers into GKE. Binary authorization is a Google Cloud service and is based on the CRITIS specification. For this to work, you must enable binary authorization on your GKE cluster where your deployment will be made. A policy is required to sign the images. When an image is built by Cloud Build and a tester verifies that it is from a trusted repository, for example, source repositories, Artifact Registry includes a vulnerability scanner that scans containers. A typical workflow is shown in the diagram. Checking of code triggers a Cloud Build. As part of the build, Artifact Registry will perform a vulnerability scan when a new image is uploaded. The scanner publishes messages to PubSub. The CRITIS signer listens to PubSub notifications from an Artifact Registry vulnerability scanner and makes an attestation if the image scanning passed the vulnerability scan. Google Cloud Binary Authorization Service then enforces the policy requiring attestations by the CRITIS signer before a container image can be deployed.
Let's now move on to consider infrastructure as code. Moving to the cloud requires a mindset change. The on-demand, pay-per-use model of cloud computing is a different model to traditional on-premise infrastructure provisioning. A typical on-premise model would be to buy machines and keep them running continuously. The compute infrastructure is typically built from fewer, larger machines. From an accounting view, the machines are capital expenditure that depreciates over time. When using the cloud, resources are rented instead of purchased, and as a result, we want to turn the machines off as soon as they are not required to save on costs. The approach is to typically have lots of smaller machines, scale out instead of scale up, and to expect an engineer for failure. From an accounting view, the machines are a monthly operating expenditure. In other words, in the cloud, all infrastructure needs to be disposable. The key to this is infrastructure as code, IAC, which allows for provisioning, configuration, and deployment activities to be automated. Having the process automated minimizes risks, eliminates manual mistakes, and supports repeatable deployments, scale, and speed. Deploying 1 or 100 machines is the same effort. The automation can be achieved using scripts or declarative tools such as Terraform, which we will discuss later. It is really important that no time is spent trying to fix broken machines or installing patches or upgrades. These will lead to problems recreating the environment at a later date. If a machine requires maintenance, remove it and create a new one instead. Costs can be reduced by provisioning ephemeral environments, such as test environments that replicate the production environment.
Terraform is one of the tools used for Infrastructure as Code, or IAC. Before we dive into understanding Terraform, let's look at what Infrastructure as Code is. In essence, Infrastructure as Code allows for quickly provisioning and removing of infrastructures. On-demand provisioning of a deployment is extremely powerful. This can be integrated into a continuous integration pipeline that smoothens the path to continuous deployment. Automated infrastructure provisioning means that the infrastructure can be provisioned on demand and the deployment complexity is managed in code. This provides the flexibility to change infrastructure as requirements change. All the changes are in one place. Infrastructure for environments such as development and test can now easily replicate production and can be deleted immediately when not in use, all because of Infrastructure as Code. Several tools can be used for IAC. Google Cloud supports Terraform, where deployments are described in a file known as a configuration. This details all the resources that should be provisioned. Configurations can be modularized using templates, which allows for the abstraction of resources into reusable components across deployments. In addition to Terraform, Google Cloud also provides support for other IAC tools, including Chef, Puppet, Ansible, and Packer. In this course, however, we will focus on Terraform. Terraform lets you provision Google Cloud resources such as virtual machines, containers, storage, and networking with declarative configuration files. You just specify the resources needed in your application in a declarative format and deploy your configuration. HashiCorp Configuration Language, or HCL, allows for concise descriptions of resources using blocks, arguments, and expressions. This deployment can be repeated over and over with consistent results, and you can delete a whole deployment with a one command or click. The benefit of a declarative approach is that it allows you to specify what the configuration should be and let the system figure out the steps to take. Instead of deploying each resource separately, you specify a set of resources which compose the application or service, allowing you to focus on the application. Unlike Cloud Shell, Terraform will deploy resources in parallel. Terraform uses the underlying APIs of each Google Cloud service to deploy your resources. This enables you to deploy almost everything we have seen so far, from instances to instance templates and groups to VPC networks, firewall rules, VPN tunnels, cloud routers, and load balancers. For a full list of supported resource types, a link to the Using Terraform with Google Cloud documentation page is included in the course resources. The Terraform language is a user interface to declare resources. Resources are infrastructure objects such as compute engine, storage, containers, etc. A Terraform configuration is a complete document in the Terraform language that tells Terraform how to manage a given collection of infrastructure. A configuration can consist of multiple files and directories. The syntax of the Terraform language includes blocks that represent objects and can have 0 or more labels. A block has a body that enables one to declare arguments and nested blocks. Arguments are used to assign value to name, and expressions, which are used to assign values to various identifiers. Terraform can be used on multiple public and private clouds. Terraform is already installed in Cloud Shell. The example configuration file shown on the right begins by indicating that the provider is Google Cloud. What follows is the configuration of a compute engine instance and its disk. The output section allows for the IP addresses of the provisioned instance to be obtained from the deployment. In this first lab, you will build a DevOps pipeline using cloud source repositories, Cloud Build, and Artifact Registry. Specifically, you will create a Git repository. You will then write a simple Python application and add it to your repository. After that, you will test your web application in Cloud Shell and then define a Docker build. Once you define the build, you will use Cloud Build to create a Docker image and then store the image in Artifact Registry. Then you will see how to automate builds using triggers. Once you have a trigger, you will test it by making a change to your program and pushing the change to your Git repo.
So let me comment variables to trigger. And we're going to save that. And then we're going to
In this module, you learned about services that you can use to help automate the deployment of your cloud resources and services. You use cloud source repositories, cloud build, triggers, and artifact registry to create continuous integration pipelines. A continuous integration pipeline automates the creation of deployment packages, like Docker images, in response to changes in your source code. You also saw how to automate the creation of infrastructure using the Infrastructure as Code tool, Terraform.
In this module, we